In this video, we'll be looking at electrical quantities. In particular, we'll be looking at potential difference, or PD, we will also look at a related quantity called electromotive force, or EMF for short. We will also look at electrical resistance, and we'll touch on Ohm's law. Now let's talk about PD versus EMF. So potential difference versus EMF. Now, what exactly is potential difference, or EMF? Now, both are similar quantities and both involve energy being converted per coulomb of charge. But in one case, energy is converted from other forms to electrical energy, whereas in the other, energy is converted from electrical energy to other forms of energy. Now, EMF is used to refer to sources. And when we speak about sources, we're talking about devices which supply electrical energy to a circuit. In other words, they convert other forms of energy into electrical energy. So these supply electrical energy. Now, when we talk about potential difference, or commonly referred to as voltage, or PD, we generally refer to devices or electrical components or circuit components which do the reverse. Well, they use up electrical energy and they convert electrical energy into other forms of energy such as light, sound, heat, etc. So PD refers to devices which basically convert electrical energy to other forms. Right? Now, if we're talking about a source, for instance, a battery, a generator, dynamo, and so on, each of these basically take some form of energy and they convert that to electrical energy. So these are sources, and when we refer to that energy conversion per coulomb of charge, we're talking about, we refer to the EMF of the source. So by definition, the EMF of the source let's call it E, or the EMF E of a source, or the EMF of a source E, is the quantity of energy W converted from other forms, and these other forms of course include mechanical energy and so on, from other forms to electrical energy per coulomb of charge. Flowing. So what exactly does this mean? If we have some source which is basically converting W energy from other forms to electrical, when a quantity of charge Q flows, the EMF of that source is given by E equals W over Q. So this equation basically gives us the EMF in terms of the energy converted from other forms to electrical energy when a quantity of charge Q flows. And from this equation, we can make W the subject for the energy, and so we get W is equal to QE. right? So we managed to define EMF, and as I said, EMF refers to the quantity of charge converted from other forms of electrical energy per coulomb of charge flowing. So if a certain amount of energy, W, is converted from other forms such as mechanical energy, could be, well, mechanical energy for instance, to electrical energy, when a quantity of charge Q flows, EMF is given by E equals W over Q, from which you can get W is equal to QE. Now if we examine the units of these quantities, the SI unit of energy is of course a joule. So if you look at this equation, the SI unit of energy is the joule, and the SI unit of charge is the coulomb. We know, of course, when we speak about EMF or voltage, the SI unit is the volt, and what this basically means is that the volt is equivalent to the joule per coulomb. So in other words, we can say that 1 volt is equal to 1 joule per coulomb, right? Now let's examine EMF. Well, not EMF rather, but PD. So we say that EMF refers to the conversion of other forms of energy into electrical energy, which is basically supplied to a circuit. And devices which do this conversion from other forms of electrical energy are referred to as sources. However, in circuits, there are also devices which do the reverse, right? They take electrical energy and they convert it to other forms like light, sound, and heat. And whenever we speak about that energy conversion per coulomb of charge, we refer to the potential difference, or the PD, across these devices. So we can say the potential difference, or the PD, across a device, or the PD, V, across a device, let's use V, is the quantity of energy W converted, or quantity of electrical energy, insert that, the quantity of electrical energy W converted to other forms per coulomb of charge flowing. Right? So the PD across a device is the quantity of electrical energy, W, converted to other forms per coulomb of charge flowing. What exactly does this mean? It means that basically, if W is the amount of energy converted, amount of electrical energy converted to other forms of energy, when a quantity Q of charge is flowing, then the PD across that device is given by V equals W over Q. So what do we say? We say that if W is the amount of electrical energy converted to other forms, when a quantity of charge Q flows the device, then the PD across the device V is given by V equals W over Q. And of course, from this, we can also see that W is equal to QV. All right? So W is equal to QV. So again, EMF refers to energy conversion from other forms to electrical energy per coulomb of charge, whereas PD refers to the conversion of electrical energy to other forms per coulomb of charge. We use the term EMF to refer to batteries, dynamos, generators, collectively called sources. These are devices which actually supply electrical energy to a circuit rather, and we use the word PD generally to refer to devices which use up electrical energy and convert it to other forms of energy. So, let's talk about electrical resistance. Electrical resistance. Resistance. The resistance, of course, comes from the word resist, which basically means to oppose. So, resistance is a synonym for opposition. So, when we speak about electrical resistance, we're talking about some form of electrical opposition to something. And what could that thing be? It's essentially due to the flow of charge, right? So when we speak about electrical resistance, we're talking about a measure of the opposition to the flow of an electric current or to the flow of charge. So electrical resistance is the opposition to the flow of electric current. Right? So electrical resistance is a measure of the opposition to the flow of electric current. Right? Now let's look at the formula. Of course, it relates electrical resistance to potential difference and current. So let's say if the PD across a device is V when an electric current I flows through it. Its electrical resistance R is given by R equals V over I. So the electrical resistance R of a device across which there's a PD V when a current I or an electric current I flows through the device is given by R is equal to V over I, which of course we can transpose to make V the subject, from which get V is equal to IR. Now this equation is occasionally referred to as Ohm's law, but of course if you're ever asked to state Ohm's law, you must state the worded form of the law and not write down the equation, alright? So this basically equation occurs as a consequence of Ohm's law, alright? And to jog your memory a bit, according to Ohm's law, the electrical current through a metallic conductor is directly proportional to the potential difference across it, provided that temperature and other physical conditions remain constant, right? So according to Ohm's law, essentially what we get is that I is proportional to V, provided temperature and other physical conditions remain constant. So what this basically means is that for a device which obeys Ohm's law, a graph of current against voltage should be a straight line. So if we say I in amperes and V in volts, for a device which obeys Ohm's law, the graph of I versus V should be a straight line passing through the origin. Of course, later on, when we look at IV characteristics, we'll examine this in greater detail. So as again, we go back to resistance. So resistance R is equal to V over I. Now what is the SI unit of resistance? The SI unit of resistance is the ohm, right? So the SI unit of electrical resistance is the ohm. And the symbol for the ohm is the Greek letter omega. So if you look at the equation to calculate resistance, R equals V over I. The SI unit, of course, of volt is, of PD is the volt. The SI unit of electric current is the ampere. And so therefore, in calculating resistance and to get the units, we divide voltage by ampere. And so what we basically see is that 1 ohm is equivalent to 1 volt per ampere. And essentially from this equation, we can actually provide a definition for the SI unit of resistance, the ohm, right? So from this, we can state that 1 ohm is the electrical resistance of a device through which a current of 1 ampere flows when the PD across it is 1 volt. So again, 1 ohm is the electrical resistance of a device across which the PD is 1 volt when an electric current of 1 ampere flows through it.